Okay, so now I'm recording. So chapter 3 deals with topics that you'd have covered already in your intro to chemistry or introductory chemistry or even high school chemistry. See if I can download that here. Dealing with, among other topics, things like the mole concept. I don't think I need to spend much time reminding you about what the term mole means in the context of chemistry. But basically, I like to tell my students that the term mole in chemistry is a counting term, pretty much similar to the term dozen that we use in everyday language, right? So everybody knows that when we talk about a dozen oranges, everybody knows that we're saying we're referring to 12 oranges, all right? So the mole is something similar, excepting that it represents a very huge number, right? So a mole of anything, one mole of anything, doesn't matter what we're talking about, that will be equal to 6.02 times 10 to the 23 of that thing, right? And we can literally apply this to anything, all right? Number of chairs, number of people, number of oranges, it doesn't matter. But in the context of chemistry, we tend to apply this term to small particles, atoms, protons, electrons, neutrons, and so on, right? And ions and so on, all right? So that's basically what we mean by the mole, right? Now, another thing that we need to remind ourselves of is what is called the molar mass, right? And the molar mass is the mass in grams of 1 mole of a substance, right? That's the definition of the molar mass, all right? So that mass we can determine based on the atomic numbers in the case of elements and the, what do you call it, the sum of the atomic numbers in a particular compound, or the molecular mass, all right? So we can get into all of that shortly, all right? Now, it turns out that, well, because of this definition, there's a relationship between the mass, the mole, and Avogadro's number. So we can simply summarize it as 1 mole, or in fact, let me continue here. 1 mole of anything is equal to 6.02 times 10 to the 23 of that thing, which would be equal to the molar mass in grams. Molar mass in grams. So that's the relationship between the mole, Avogadro's number, which is what this is, by the way, Avogadro's number, right? That will be equal to the molar mass, or equivalent to the molar mass in grams, all right? So the reason I'm mentioning all of this is because knowing this is key to answering question number 1. So question number 1 says complete the following conversion. Now the first one is moles of 0.00515 grams of water. So the way we go about doing this is that we start off with the 0.00515 grams of H2O. And to convert it to moles, we have to multiply it by a conversion factor, which allows you to go from from grams to moles, and that would be the molar mass. So how do we get molar mass? We go to the periodic table and we look up the molar mass of hydrogen multiplied by 2, and then we add the molar mass of oxygen. So hydrogen, just going to do a quick calculation here. Hydrogen would be 2 times 1.008, and then we add to that 16. So that gives you 18.016 grams. So therefore, that would be the molar mass. So the way we represent it here is that we put the 1 mole of H2O above as the numerator, and down here we put the molar mass in grams, 18.016 grams of H2O below, so that these units will cancel out. So the only unit you'll be left with would be the moles of water, and then all we have to do would be the number crunching, which would be .00515 divided by 18.016. And according to my calculation, we have to round this up to 3 sig figs. So according to my calculation, the answer becomes 2.86 times 10 to the minus 4 moles. And that's how we do it. All right? That's a relatively simple example. Any questions about this one? Any questions? Okay, in the case of the next one, you're given 3.50 moles of sodium hydroxide, and you're asked to determine the number of atoms present in this amount of sodium hydroxide. All right? So basically, we're going to start off with 3.50 moles of NaOH, and we're trying to find the number of, we're trying to find the number of atoms present. All right. All right. Okay, what's going on? Okay, so in this particular case, the way I would go about solving this is I would start off with the moles of sodium hydroxide. All right. And then I would find out, based on that, the number of formula units of sodium hydroxide. Formula units basically is referring to the number of sodium, oxygen, and hydrogen units that are present in the compound. And then based on this, we can find out the number of atoms present in this amount of sodium hydroxide. So the way we're going to do that, well, firstly, let me say that based on what I have here, this will require, this transformation here, would require 2 conversion factors, one for the first step and the other for the second step, all right? So 3.50 moles of the sodium hydroxide we're going to start off with, and to get the formula units, that's where Avogadro's number comes in, right? So we're going to put 1 mole of sodium hydroxide below, and above I'm going to put 6.02 times 10 to the 23 formula units of sodium hydroxide, all right? And then the next conversion factor is where we go from the number of formula units to the number of atoms. And based on the formula for sodium hydroxide, there are 3 atoms. There are sodium, oxygen, and hydrogen, right? So therefore, for every formula unit of sodium hydroxide, there are 3 atoms present. And that's it. That's the setup. So, 3.50 times 6.02 times 10 to 23, and then multiply by 3. So according to my calculation, I got 6.32 times 10 to the 24 atoms. And that's basically how that is done. All right. Any questions about this one? Questions out there in Zoom? Okay, is it okay for me to clear this? All right, let me clear this, because I need to scroll down to the next question. So let's see if you can do C. Let's hear what you have to say about C. In the case of C, they gave you 2.50 moles of oxygen, O2, and that's important. The fact that you have 2 oxygen atoms per molecule, right? And you're asked to determine the grams of O2 present, all right? So how would you do this problem?
1 mole of O2.
Okay, let's start off with this first.
Okay.
What do you multiply this by?
1 mole of O2.
Where does that go? The top or bottom?
Bottom.
Okay, 1 mole of O2 below, and what goes above?
Avogadro's number.
No, because you're not trying to find the number of molecules.
Oh,
You're trying to find the mass in grams.
then the grams of the oxygen.
Right, so basically,
32.00.
exactly, 32.00 grams. of O2. And somebody said something in the chat. Let me see what this person said. Yes, what, yeah, somebody here is agreeing with you. Okay. So that's it, pretty much. So let's see what this gives. 2.5 times 32. And according to my calculation, this will be rounded off to 368, so therefore 80.0 grams of O2 would be the answer. All right. Okay, any question about this one? Any questions? Any questions? Okay. B. They're asking in the case of B, the number of carbon atoms in 10.5 grams of this compound, right? So you're starting off with 10.5 grams. There's a sheet going around. Make sure you sign. Oh. There's the sheet. 10.5 grams of C6H12O6, and they're asking for the number of carbon atoms. Okay, so let me hear what you have to say about this one. How would you solve this one? We're going to start off with what we're given, 10.5 grams of C6H12O6. What would you multiply this by first thing?
Sorry, go to everybody.
Yeah, I think everybody has signed up. Yeah.
I should be assigned.
That-
The assignment, this.
Oh, yeah. Oh, you didn't get one?
Yeah.
Oh, I'm sorry, my bad, my bad. Yeah, she didn't go. Yeah. Okay, so, what's the first step in this problem, to solve this problem? Start off-
Avogadro's number.
Oh, Avogadro's number? Not yet. It will come along later on, but now we need to, because remember, Avogadro's number, you use to convert from moles to the number of atoms or vice versa. Right now, we're starting off with grams.
So would you convert it to moles, so we.
Convert it to moles, exactly. So down here, well, up here, you're gonna have 1 mole of C6H12O6. And down here, the molar mass. So, of course, me being the lazy person I am, I'm going to go to my trusty molar mass calculator. So go down here. C6H12 and calculate, and 180.16 is the molar mass of C6H12O6. So that would go down here, 180.16 grams of C6H12O6. All right. Okay, so let me get back to assignment here. Okay, so that's the first step. So this will cancel out with this, all right? So up to this point, we would have the moles. And then, as the young lady out there in Zoom said, she mentioned Avogadro's number, that can come into play here, right? Because we have the mole value here. We can find the number of molecules in 1 mole, which is Avogadro's number. So the way we will set this up here is that we're going to have 1 mole of C6H12O6 down here as the denominator. And up here, 6.02 times 10 to the 23 molecules of C6H12O6. All right. So that this will go with this. All right. But we're not finished yet, because remember what the question is asking for is what? The number of carbon atoms. So far, we have determined the number of molecules, right? So how will you get from molecules to the number of carbon atoms?
Would it be how many carbon there are compared to the whole
Okay, so,
amount?
okay, yeah, okay. You're onto something. So how would you represent that here?
You would do 24 on the bottom and 6 on the top.
24, where do you get 24 from?
12 plus 6 plus 6.
No, that wouldn't be it. You're right about the 6 carbon atoms on the top. I would agree with you there. 6 C atoms above. But what would you put down here? Anybody?
One.
1 molecule.
Oh, okay, I understand.
See what I'm saying?
Yep, there's 6 in every one.
Exactly. So that this will go with that, right? And then we do the number crunching. 10.5 divided by 180.15 times 6.02 times 10 to the 23 times 6. And according to my calculation, I got rounded off to 3 sig figs, 2.10 times 10 to the 23 C atoms. So that's basically how that is done. In fact, let me correct that. I should be 2.11. 2.11 times 10 to the 23. All right, any questions about it? Any questions? Any questions out there in Zoom? Any questions? No questions? All right, so as I said before, this is a bit of a review of stuff that we have done in introductory chemistry, high school chemistry, whichever. Let me clear this and scroll down to see what's next. Oh, okay, now this one is dealing with percentage of elements in a compound based on the molecular formula. Basically what you're asked to do in the A part and B part, let me see what the B part says. And the C part, okay. What I'm going to do is just do the A part. It's pretty simple. And I leave you to do the others on your own, right? So in the A part, they gave you the formula for benzoic acid, and they're asking for you to calculate the percent composition, right? Basically what they're asking for is a percent of each element present per molecule of compound, right? So in the case of carbon, to get the percentage of carbon, you take the molar mass of carbon, which is 12.01 grams per mole. And because you have a 7 here, you multiply that by 7. And then you're going to divide that by the sum total of the molar masses of everything. Again, I'm going to go to my molar mass calculator. What was the formula? C7H6O2. Okay, so C7H6O2. 102.12. So that will go, what did I do? So 122.12 grams per mole times 100%. All of this here, after you work it out, you multiply by 100%. All right. So let's see what that gives. 12.01 times 7 divided by 122.12, and then I multiply by 100%. And according to my calculation, rounded off to 3 sig figs, is going to be 68.84%. And that's it for carbon. And we do the same thing for the others. So let me do that now for the hydrogen. The percent of hydrogen will be equal to the molar mass of hydrogen is 1.008 grams per mole, multiplied by 6 for the hydrogen, and then divide that by, again, 122.12 grams per mole. And again, we multiply all of this by 100%. So let's see what this gives. 6 times 1.008, and then divide by 122.12, and times 100. And according to my calculation, this works out to be equal to 4 sig figs again, so 4.953% is what I got. All right. So that's for hydrogen. And again, we do the same thing for the oxygen. So percent oxygen will be equal to, so in the case of oxygen, the molar mass is 16.00 grams per mole, multiplied by 2, and then we divide by, again, 122.12 grams per mole, and then we multiply by 100%. And let's see what that gives. So that gives 32 divided by 122.12 times 100. And according to my calculation, this works out to be equal to 26.8 0.20, I'm sorry, 0.20. All right, percent. And that's how you do that, right? And what I recommend when you're doing problems like these, check to make sure that these add up to 100%, right? Because if it does add up to 100%, that means you did something wrong in your calculation. So if you add 68.84 plus 4.953 plus 26.20, okay, I did something wrong. 68.84 plus 4.953 plus 26.20. Okay, so I got 99.99, which is almost 100%, right? So I would recommend that you do that kind of check when you're doing problems like this, right? Okay, any questions about this one? Any questions? And the approach would be very similar for the others in that question. We just did the A part, the B part, and the C part, pretty much the same idea. All right, so I'm going to leave that for you guys to do on your own. If you have any problems with any of those, feel free to contact me, and I'm more than willing to help you. All right, so let me clear this here. And then scroll down. So that's B for you to do, C for you to do. Okay, now this is more challenging than what we just did, because what we just did was that based on the formula, we determined the percent composition of the different elements present. In this case, we're doing the reverse. You're given the percent compositions, and you're asked to determine, in this case, the empirical formulas, right? Now remember, there's a difference between the empirical formula and the molecular formula, right? The molecular formula gives you the number of atoms of each element present per molecule. The empirical formula gives you the simplest ratio of the atoms present in a substance. So for example, the last one we just looked at, well, not the last one, the C6H12O6 is a good example of this. We looked at earlier. So the molecular formula is C6, oops. C6H12O6, right? That's the molecular formula for that compound. The empirical formula would give you the simplest ratio, which would be CH2O, right? The molecular formula tells you that in this case, for this molecule, there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, right? So it gives you the number of atoms of each element present in the molecule. But the empirical formula gives you the ratio of carbon to hydrogen to oxygen, which is 1 to 2 to 1, right? So it's important that you know the difference. And what we're going to do is we're going to use the percent mass data that you see here to determine the empirical formula, right? You can only determine the empirical formula directly from the percent composition data, right? In order for you to get from the empirical formula to the molecular formula, you need more information. We're going to get into that later on, right? But for now, we're going to work this example here, or this question, where we're going to determine the empirical formula based on the data that's provided here. So let me clear this. Okay, so the question says, it gives you the percentages of carbon, hydrogen, nitrogen, and oxygen. 62.1% carbon, 5.21% hydrogen, 12.1% nitrogen, and 20.7% oxygen, all right? So basically, the first thing that we should do is, when you're solving problems like these, is that we assume that we're working with 100 grams of the compound, right? Because when you assume that, basically that means that these numbers would represent the mass in grams for 100 grams of the compound, right? So we make that assumption. Now you could assume literally any number, right? You could assume 25 grams, but what you'd have to do is multiply the 25 grams by the percentages to get each of the masses of the different elements. 100 grams is a nice round number, which means that you don't have to do any complex calculation. You just basically assume 100 grams, which means that these numbers would represent the mass in grams of each of these elements, right? Now, if you have had me before, you know that I like to solve problems like this in a tabular fashion, in the form of a table. So at the top of the table, I'm going to put the formula for the different elements. Carbon here, hydrogen here, nitrogen here, and oxygen, right? So these are the elements that I've placed at the top of the table. And because we have assumed that we're working with 100 grams of the compound, I'm going to create a row here for the mass of each element, right? So we assume 100 grams of the compound, which means that the mass of carbon is 62.1 grams. The mass of hydrogen is 5.21 grams. The mass of nitrogen is 12.1 grams. And the mass of oxygen is 20.7 grams, all right? So that's the first row, right? The next row, we're going to convert each of these masses to their corresponding mole value. How do we do that? Well, this is something you should be familiar with. All you have to do is take each mass and divide them by their respective molar masses, right? And the molar masses, of course, we can get from the periodic table, right? So we take the 62.1 grams and we multiply by 1 mole over the molar mass of carbon, which is 12.01 grams. We do the same thing for the hydrogen, 5.21 grams. We multiply that by 1 mole over 5.21 grams. And then in the case of nitrogen, 12.1 grams, we multiply that by 1 mole over 14.01 grams. And then in the case of oxygen, 20.7 grams, multiplied by 1 mole over the molar mass of oxygen, which is 16.00 grams, all right? So we have to work out each of these. All right, starting with the carbon, and folks, please correct me if I've made any mistakes, right? So I would suggest you do the same calculations along with me. So if I make a mistake, you can point it out to me, all right? All right, so 62.1.
Under the 5.21,
Uh-huh.
the 1 mole, what's the denominator?
There you go. I made a mistake right there. This should be 1.008.
Oh,
Yeah, my bad. So you see, that's the reason why you guys need to correct me when I make errors, all right? Okay, thank you. So I was doing the carbon, right? 62.1 divided by 12.01. So I got 5.17 when rounded off to 3 sig figs moles. And then in the case of hydrogen, I divide 5.21 divided by 1.008, and I got 5.17 again. All right. And then in the case of nitrogen, I'm going to take the 12.1 and divide it by 14.01, and I got 0.8, how many sig figs? 3 sig figs, so that's 0.864 moles. And then finally, in the case of oxygen, 20.7 divided by 16, and I got 1.29 moles, all right? So that's basically how you get the mole values. You divide each of the masses by their respective molar masses. Okay, the next step is where we find the simplest ratio. Now, how do we find the simplest ratio? We look at each of these numbers I'm circling here, each of these numbers, and we decide which one is the lowest one, which is this one right here. This has the lowest value, right? And what we do is divide all of these numbers by that lowest value. So here we're dividing by 0.864 moles, right? So starting off with the 5.17 moles divided by 0.864 moles. Let's see what that gives. 5.17 divided by 0.864. So according to my calculation, this works out to be 5.98 when rounded off to 3 sig figs. And this is the same thing, 5.17 moles divided by 0.864 moles. And that's also equal to 5.98. All right. And please note, at this stage, the mole units cancel, right? So this value here has no units. The 5.98 has no units. Same thing is true here. And this divided by itself will give you 1. And then here, we're going to have 1.29 moles divided by 0.864 moles. So let's see what that gives. 1.29 divided by 0.864. And for this, rounded off to 3 sig figs, I got 1.49 as the answer for that part, right? Okay. Now, in some cases, when we get to this stage, what we would do is round off to the nearest integer, right? So for example, these 5.98 here, we round off to 6. However, the 1.49 here is not close to any integer, right? So we can just simply round off to the nearest integer, right? So what we'd have to do is multiply this number by an integer, which converts it to a number, which is itself an integer, all right? Now, 1.49 is close to 5, so one can surmise that, okay, if you multiply 1.5 by 2, you're going to get an integer, which is 3. So what that means is that we need another row, which I don't have space for here. So let me erase the top part here. All right, so I'm just going to continue up here. So basically what I'm going to do is multiply these values by 2, right? So 5.98 times 2, that gives you 11.96, and you're going to have 11.96 here as well. And 1 multiplied by 2 will give you 2, and 1.49 multiplied by 2 will give 2.98. So now we have some numbers that we can round off to the nearest integer because they're close to the nearest integer, right? So the 1.96, you can round it up to 12, and 12 here. And this will be still 2, and this now you can round off to 3, all right? All right, so now these numbers will serve as the subscripts in the empirical formula. So I'm going to write the empirical formula here. So the empirical formula would be C12, H12, N2, O3. And that would be the empirical formula based on the data that is given. All right. So that's a typical empirical formula type of question. Very typical. All right. Okay. Any questions about this? Any questions? Any questions? Any questions? Any questions out there in Zoom? Okay, so let me clear all of this here. And let me scroll down to, okay, so you should be able to do based on what we have just done before. In fact, this problem is actually easier, right? So based on what we have done before in A, you should be able to do B. Let me look at C. And C, you should be able to do that as well. Okay, so I'm going to leave those for you to do on your own. Again, if you have any problems doing them, let me know, all right? Now, the next thing we're going to talk about is this whole idea of combustion analysis, right? This is basically a technique that is used to analyze the composition of organic compounds, right? I don't know if you know what organic compounds are. By definition, organic compounds are basically compounds of carbon, and there are some exceptions like carbonates and isocyanates and so on. But basically, most organic compounds contain carbon and hydrogen, and some may contain oxygen and other elements like nitrogen, sulfur, and halogens and so on, right? So, what we'll be talking about here is how do we analyze an organic compound by way of combustion analysis. So let me just briefly go over what combustion analysis is all about. So let's say you have an organic compound, and let's say that compound contains carbon, hydrogen, and oxygen, right? You don't know what the formula is, right? And then you burn it in air. Now, that's combustion, right? Combustion is basically reacting anything in air by applying heat, right? In the case of organic compounds, like the hypothetical example we're talking about here, if you have a compound that contains carbon, hydrogen, and oxygen, then the products will always going to be CO2, gas, and H2O, gas, all right? So if you burn any organic compound that contains carbon, hydrogen, and oxygen, then you're going to get those products, right? So basically, if you can find some way of trapping the products and weigh them, right? And then you can find out the mass of carbon in carbon dioxide and the mass of hydrogen in water. Then you can go back and determine, well, basically the mass of carbon here will be the same as the mass of carbon here, right? And the mass of hydrogen here will be the same as the mass of hydrogen here, right? Now, as far as the oxygen is concerned, you can get that by taking the total mass of the compound and subtracting the mass of carbon and hydrogen from it, and that will give you the mass of oxygen, right? And therefore, based on those masses, you can determine the empirical formula, right? So that's basically an overall description of how combustion analysis works, right? Now, in this case, it says that you're burning 12.501 grams of a compound, and it produces 38.196 grams of carbon dioxide and 18.752 grams of water. Our previous analysis determined that the compound does not contain oxygen. So in this particular case, there are no oxygens in that compound, right? But that doesn't change the product outcome in terms of what is produced. You're still going to end up with carbon dioxide and water, right? So the question is asking for you to establish the empirical formula for the compound. All right, so the first thing we're going to do is to find the mass of carbon. The question gives us that the mass of carbon dioxide is 38.196 grams, right? That's the mass of carbon dioxide. Now, based on the formula for carbon dioxide, we can conclude that for every mole of carbon dioxide that's present, you have 1 mole of carbon. So therefore, we can find the moles of carbon dioxide. I'm sorry, I just made a mistake. The first thing we need to do actually is to find the molar mass and find moles, right? So the molar mass of carbon dioxide is 44.01 grams, right? So 44.01 grams of CO2, right? Down here and up here, we're going to have 1 mole of CO2, right? So that's the first thing, right? You need to find the moles of carbon dioxide. And then what I was about to say is that based on the moles of carbon dioxide and based on the formula, we can see that for every 1 mole of carbon dioxide, there's 1 mole of carbon. All right? So up to this point, we would have determined the moles of carbon. These are the units that will cancel out, the grams of carbon dioxide and the moles of carbon dioxide, right? The next step is to find the moles, the next step is to find from the moles of carbon, the grams of carbon. So that means that we have to multiply by 12.01 grams of carbon over 1 mole of carbon, all right? So let's do that calculation, 38.196 divided by 44.1 times 1 times 12.01. And according to my calculation, this works out to be equal to 10.42 grams of carbon, all right? Excuse me. So the mass of carbon that we just calculated here is the mass of carbon in the carbon dioxide, which would be the mass of carbon in the original compound, all right? Then we do a similar calculation in the case of water, right? So we're going to start off with 18.752 grams of H2O. And like we did before, we find the moles. So 1 mole of H2O would go up top, and the molar mass of water is 18.02 grams, right? So this will cancel out with that. And then the next step, and let me just emphasize this step here, because the next step is where students oftentimes make a crucial error, right? Remember here in this equivalent step, we said that 1 mole of carbon would be in 1 mole of carbon dioxide, right? And that's based on the formula, right? Well, based on the formula for water, for every 1 mole of H2O, there are 2 moles of hydrogen. This, I can't tell you how many times over the past years, students keep making the same mistake. They assume that this is 1 mole of hydrogen, right? But it's 2 moles of hydrogen for every 1 mole of water, right? So please make a note of that, right? So this will cancel out with that. And then the next step is where we go from moles of hydrogen to the mass of hydrogen, which is 1.008 grams of hydrogen. So that this cancels out with that. And then we do the number crunching, 18.752 divided by 18.02 times 2 times 1.008. And according to my calculation, this works out to be equal to 2.09. I'm sorry, 2.0. all right, 2.098 grams of hydrogen, all right? And I just realized something here, but let me not talk about it right now. I'll mention it later on. Okay, so we have found the mass of carbon, we have found the mass of hydrogen. There are no oxygens present. Now, what you typically do if oxygen was present is add these two and subtract it from the original amount. But in this case here, if you add the 10.42 to the 2.098, sorry, 10.42 plus 2.098, you're gonna get basically the same as this mass right here, all right? Now, I was about to say that I really did not need to do this next step, but it won't hurt the exercise in any case, all right? So now that we have the masses of carbon and hydrogen, all we have to do is do like we did before in the previous example. In other words, I need you guys to remember these numbers when I erase it, because I'm going to use it in the next table. I need to clear this to make some space. So carbon, hydrogen, masses, right? So what was the mass of the carbon?
0.42 grams.
10.42 grams. And what was the mass of the hydrogen?
0.098.
2.098, okay, grams, all right? So if you remember what we did before in the previous question, what was the next step? After we have the masses, we find the moles, which means that we have to divide each of these by their respective molar masses. So in the case of carbon, that would be 1 mole over 12.01 grams. In the case of hydrogen, that would be 2.098 grams multiplied by 1 mole over 1.008 grams. And we work these out. So 10.42 divided by 12.01. So this gives 0.868 moles. And then in the case of hydrogen, that's 2.098 divided by 1.008. And this gives 2.08 moles. Okay, so we have the mole values. What's the next step? Based on what we did before in the previous example.
Divide by the lowest.
Exactly, which would be the 0.0, which would be the 0.860. 0.868, I'm sorry. So divided by 0.868 moles. So this will give you 1, and then 2.08 moles divided by 0.868 moles. So let's see what that gives. 2.08 divided by 0.868. Okay, so this gives, okay, so this gives 2.40. We're rounding off to 363. So I rounded off too early here. Let me do this one. 2.098 divided by 1.008. Okay, so this should be 2.081. And 1 should be here. I don't think it will change the end result divided by 0.868. Okay, yes, so I still get 2.40, all right? Now, again, 2.40 is a number that is not close to an integer, so we can't just round off to the nearest integer, right? So we have to, in this particular case, we have to play with some numbers, right? Because we have to basically multiply the 2.40 by an integer, which converts it to an integer. So if I do 2.4 times 2, 4.8, maybe 2.4 times 3, 7.2, maybe 2.4 times 5. Oh, that gives you exactly 12, right? So basically, the next line if I can squeeze it down here, is where you multiply right through by 5, right? So when you multiply right through by 5, you're gonna end up with 5 carbons here and 12 hydrogen. So therefore, the empirical formula in this case would be C5H12. And that's basically how that would be done. Okay, any questions about this?
Can you move a little bit because I can barely see it for the ×5?
I'm sorry?
For the ×5 part, I can barely see it for the H.
Or which,
Or is it just 12?
Where?
No,
It's just 12.
oh, you mean this here?
Yeah.
Oh, that's 12.
yeah, I thought you did like you showed the math, but
No, I multiplied the 1 here and the 2.40 here by 5, which is what I have here. So 5 times 1 gives you 5, 5 times 2.40 gives you 12. Excuse me. So therefore, the resulting empirical formula will be C5H12. Right? Okay. Oh.
Just as an example, because when you were going through the multiples and you were like, maybe for 2.8.
Right, exactly.
For that, if you did go with the maybe, it would give you a different answer, so do you always have to pick the one that lands on the exact digit?
Or as very close to as possible.
Okay.
Right. In this case, it just works out to land exactly at 12. So that's the best one of all the other options that we
So,
would try.
so you went around it, if it's 0.8, it would have to be 0.9, or is that?
Yeah, if it was something like yeah, if it was something like 0.8, yeah, or 0.9, yeah. Things get tricky now when you get to 0.7 and, you know, below, exactly, so. Okay, so that's number 4. Let me clear this here. And let's see what's next. Okay, number 5, again, is combustion analysis. They gave you the masses of carbon dioxide and water, and it says again, the compounds contains only carbon and hydrogen. All right, so it's kind of similar to what we did before, but I'm going to do something slightly different because this compound contains only carbon and hydrogen, which I probably should have done in the previous example, but we still ended up with the right answer. And it gives you the monomass, and the question is asking this time for the molecular formula. All right, so like before, I'm going to start off with the 5.86 milligrams of carbon dioxide. And what I will do first is convert this to grams. So here we're going to have 1 gram of carbon dioxide. Down here we're going to have 1,000 milligrams of carbon dioxide. All right. And then the next step is to convert from grams to moles. So I'm going to have 1 mole of CO2 above and 12.01 grams of CO2 below, right? Now, in the previous question, I continued to find out, oh, actually, let me do this. So the next step would be 1 mole of carbon dioxide below and 1 mole of carbon above, all right? So in terms of unit cancellations,
Professor,
yeah,
would it be 12.01, or would it be?
44.01, thank you, yeah. 44.01, so 44.01 grams, thank you. Okay, so as I was saying, this will cancel out with that, this will cancel out with this. All right, now in the previous question, I went on to determine the mass of carbon based on the moles. But when it comes to compounds containing carbon and hydrogen only, we don't need to do that. You're going to see why shortly. But let me just do this calculation right here. So 5.86 divided by 1,000 divided by 44.01. So here I got 1.33 times 10 to the minus 4 moles, all right, of carbon. And then we do something similar in the case of water, starting with 1.37 milligrams of H2O. We convert that to grams, so we're gonna have 1 gram of H2O over 1,000 milligrams of H2O. And then here we're gonna have 1 mole of H2O. Actually, 2 moles of, 1 mole of H2O over the molar mass, which is 18.02 grams of H2O. And then the next step, as I said before, you have to be careful about, you're gonna have 2 moles of hydrogen over 1 mole of H2O, all right? Again, we have this 2 here because of the molecular formula where we have 2 as a subscript for the hydrogen, all right? And again, because the compound contains only carbon and hydrogen, we don't need to calculate the mass of the hydrogen in this case. So let me do this, 1.37 divided by 1,000 divided by 18.02 times 2. So according to my calculation, this works out to be equal to 1.52 times 10 to the minus 4 moles, all right, of hydrogen. So because we have the moles of hydrogen and the moles of carbon, and those are the 2 elements that are only present in the original compound, then what we can do is use these values at the top of the table that I'm about to set up, right? So what I'm gonna do is clear this. If it's okay by you, then I clear it. So let me clear this. And I'm gonna set up my table, carbon, hydrogen. And the first row, instead of mass, we're going to have mole because we just calculated those. For the carbon, it's 1.33 times 10 to the minus 4 moles. And for the hydrogen, it's 1.52 times 10 to the minus 4 moles. And then we divide right through by the lowest mole value. So we divide by 1.33 times 10 to the minus 4 moles. This divided by itself will give you 1. And then we have 1.52 times 10 to the minus 4 moles divided by 1.33 times 10 to the minus 4 moles. So when we do the calculation of 1.52 times 10 to the minus 4 divided by 1.33 times 10 to the minus 4, the answer I got is 1.14. Right? So again, this is one of those situations where you have to try different numbers to convert that into an integer. So the next row, I did this already myself, so I know what that integer is. And it's 7. Because when you multiply 1.14 by 7, I got, in this case, 7.98. This is 7, and this is 7.98, which is very close to 8, right? So the empirical formula is C7H8, all right? But we're not finished yet because the question is asking for the molecular formula, right? Now, basically, to get a molecular formula, you need to find what is called the empirical formula mass. The empirical formula mass is based on the addition of all the molar masses of the empirical formula. So, if I go back to my molecular weight calculator, we're trying to find the empirical formula mass of C7H8, and that is 92.14, right? So this is going to be 92.14 grams per mole, right? Now, to find what is called the integral factor, I, that's an integer which basically relates the empirical formula mass to the molar mass.
Wait, sorry, where did you get 92.14?
By adding up the molar masses of
Oh,
C7H8, right? So I is equal to the molar mass of the compound divided by the empirical formula mass, right? Now, it turns out that the molar mass is 92 grams per mole, and the empirical formula mass is 92.14 grams per mole, right? So this is basically approximately equal to 1, right? And because this is approximately equal to 1, that means that the empirical formula will be the same as the molecular formula, which is C7H8. And that's the answer for that question. Right? Okay, any question about this one? Any question? Any questions out there in Zoom? All right, so, okay, can I try this? Alright. Okay, let me see what the next question is. Okay, so I'm gonna leave number 6 for you to do. Number 7. Now, number 7, you have to be careful because number 7 contains carbon, hydrogen, and oxygen, right? So the approach will be slightly different. So I'm gonna leave that for you to look at. If you have any questions, of course, please feel free to contact me, all right? Okay, number 8. Again, this is harkening back to what you learned in high school chemistry, introductory chemistry. Balance and complete the following equations, right? So how would you balance the first equation? Remember, when you're balancing equations, the only thing you should be adjusting are the coefficients. Right, the coefficients, those are the integers that are placed in front of the formulas for the different compounds, right? You cannot change the formula for the compound by adjusting the subscripts. Right? That would be incorrect. So how would you balance the first equation? 8A.
Start with carbon.
Okay, let's start with carbon. We have 5 carbons here, so what do you do over here?
Put a 5.
Put a 5 in front of the CO2. And let's look next at the hydrogens. We have 10 hydrogens here. So what do we do on this side here?
5.
Here. And then we look at the oxygens, right? How many oxygens do we have total on the left side? 4. How many do we have total on the right side? 50. All right, so how do we balance the oxygens?
You have to double everything on the right and put a 2 in front of the C5H10O2 and then put 5 on the O2.
You were right up until
The
the
last one, yeah.
so this is what I would do, right? To balance the oxygens, what I would do is put 13 over 2 here, right? And the reason why I would do that is because 13 over 2 times 2 gives you 13, which adds to 2, which gives you 15, which balances with the 15 on the right side, right? But I wouldn't leave it like that because we typically, conventionally, have to have integers for all the coefficients. So what I would do to convert the 13 over 2 is multiply everything by 2 to convert 13 over 2 into an integer. So the final answer would be 2C5H10O2 plus 13O2 to give 10 CO2 plus 10 H2O. And that's how I would do that. All right. Okay, any questions about this one? Any questions? Questions? Okay, what about B? How would you balance B?
It would be PCl5 plus 4O2 equals H3PO4 plus 5HCl.
For H2O and what goes here?
Nothing.
And what goes here?
5.
5. So let me see, phosphorus is balanced. Balance, 8, yep. Okay, I would agree with that, yep. Okay, so that's basically how that is done. All right, in the interest of time, I'm gonna leave the others for you to do as well. I want to get through as much of this as possible, so I'm gonna leave 8, C and D for you to do. And number 9 as well, I'm gonna leave number 9. Again, number 9 deals with balancing equations. In this case, they're asking to balance the equations based on the word descriptions that they gave, all right? So you should be able to do those as well. Okay, let me do number 10, at least the A part, all right? So number 10, they gave you the balance equation here. And they said, or they're asking, how many moles of carbon dioxide are produced when 1.50 moles of octane reacting? Octane is C8H18, right? So based on the balance equation, if you look at the relationship between the O2 and the octane, there's a 2:16 ratio between the octane and the CO2. So, what I would do is start off with the 1.50 moles of C8H18. And then I would multiply by a conversion factor, which represents the mole relationship between the carbon dioxide and the octane. That is 16 moles of carbon dioxide over 2 moles of C8H18. Right? And then I'll do the number crunching. So that's 1.5 times 16 divided by 2. So according to my calculation, this works out to be 12.0 moles of O2. All right? And that's basically how that is done. Okay, relatively simple problem. And the B part is again relatively simple, a bit more challenging than the A part. In this case, it's asking for how many grams of water are produced in this reaction. So again, I would start off with the 1.50 moles of C8H18. But this time I would look at the relationship between the water and the octane, right? So in this conversion factor, I put 18 moles of H2 above and 2 moles of C8H18 below. So that would give us the moles of water. And then the next step is that I'll convert the moles of water to the grams of water. And that's where the molar mass comes in. So down here, I'm going to put 1 mole of H2O. And up here, I'm going to put the molar mass of water, which is 18.02 grams of H2O. So 1.5 times 1.8 divided by 2 times 18.02. So according to my calculation, this works out to be equal to 243 grams of H2O. And that's how.
Let's say 18.0.
Oh, 18.02, yeah. And that's how that is done. All right,
243.
243 grams, yeah. Okay, is it okay for me to clear this?
Yeah.
Let's see what's in store further down. Okay, I'm gonna leave you guys to do C. If you understood what we have done before, you can do C. Let me see what is this. Okay, in the case of number 11, I'm not sure if we'll have enough time to do this, but I'm going to at least start. It says in a certain experiment, 2.50 grams of ammonia reacts with 2.85 grams of oxygen to produce NO2 and H2O. Which reactant is the limiting reactant? All right, so in order for us to do a question of this type, statistical stoichiometric type problem, we need to find out what the balance equation is based on the information provided, right? So let me ask you this, based on the information provided, what are the reactants?
NH3 plus O2
NH3 plus O2. And what are the products?
equals NO2 plus H2O.
Exactly, all right. And then we have to balance it. So how would you go about balancing this equation?
So it would be 2 NH3 plus 2 O2 equals 2 NO2 and 3 H2O.
Okay, not quite,
Nope, I missed it. Sorry.
not quite. You're on your way there, but this is not the answer, because based on what we have here, the oxygens will not be balanced. All right, you have 4 oxygens here, you have 4 plus 3, 7 oxygens, all right? So what I would do is something similar to what I showed you earlier. Let me take those numbers out. I will start off with the nitrogens, right? We have 1 nitrogen here, 1 nitrogen here, so I'll leave that alone for the time being. We have 3 hydrogens here, and we have 2 hydrogens here. What I would do to balance the hydrogens is put a 2 here and a 3 here, right? So that would be 6 hydrogens on either side. And because I put a 2 here for the nitrogen, that means I'll put a 2 here. Now the problem is the oxygen, because on this side we have 2 oxygens on the left side. On the right side, we have 4 plus 3, 7 oxygens. So what I would do is something similar to what I showed you earlier. I'll put 7 over 2 here, right? Because 7 over 2 times 2 gives you 7, which balances with the 7 oxygens on the right, all right? And then what I will do next, as I showed you before, is multiply right through by 2. So here you're going to end up with 4 NH3. Here you're going to end up with 7 O2. Here you're going to end up with 4 NO2. And here you're going to end up with 6 H2O. And that would be the balanced equation. So this is something that you'd have to do first before you can do anything else, right? You have to start off with a balanced equation before you can actually get into the actual calculation part. All right, so with that said, let's start off with the 2.50 grams of the ammonia, right? What I would do is find out how much of either of these products, it doesn't matter which one, right? How much of either of these products will be produced based on the 2.5 grams of ammonia. So the first step is that we need to convert from grams to moles. So we're gonna have the molar mass. So let me go again to my NH3. So that's 17.03. So let me go back to here. So that would be 17.03 grams of ammonia. And then I'll multiply that by, okay, so I'll look at the mole ratio between the ammonia and the nitrogen dioxide. That would be 4 moles of NO2 above and 4 moles of NH3 below, all right? This thing is laggy. Okay, so 2.5 divided by 17.03 times 4 divided by 4. So the answer I got here is 0.147 moles of NO2, right? And then I'm going to do something similar, starting with the 2.85 grams of oxygen. So I would multiply that by 1 mole of O2 above and 32.00 grams of O2 below. And then here, I'm going to have 4 moles of NO2 over 7 moles of O2, because that's the mole ratio between the O2 and the NO2, right? And I would work this out. So 2.85 divided by 32 times 4 divided by 7. And according to my calculation, this works out to be 0.0509 moles of NO2, right? Now,
I'm a little confused. The first conversion factor you used, what's in the denominator?
here,
Yeah, the
4 moles.
Oh, no, sorry, the 2.50, is it O2? So I was.
Oh, yeah, 2.502, right? And this, I'm multiplying by 1 mole of O2 over the molar mass of O2, which is
Okay.
32.00 grams, right? Okay, so at this stage, what we do is compare these two numbers, and we decide on which one has the lowest value. And the answer is this one right here, right? So because this one has the lowest value, or the lower value, that means that the oxygen would be the limiting reactant. All right? And that's in answer to this question right here. The question was asking, which reactant is the limiting reactant? And the answer is the oxygen, because based on the calculations here, on paper, we would expect a lower amount of the NO2 produced based on this reaction, right? Compared to ammonium. So therefore, oxygen is the limiting reactant. Okay, I'm going to stop here because it's now 10:42. And I'm going to continue this discussion next week. In the meantime, let me clear this here. I'm going to publish the videos for the next chapter. So let me go to modules. Okay, so let me publish chapter 4. All right, so make sure you watch those videos, and also you can attempt the other questions. Let me see how many questions are left in this assignment. Okay, so we did up to part of 11, so there's 11, 12, 13, 14. Actually, up to 20. In fact, hold on. I just realized that 20 is an error. I'm going to make that change and get back to you on that. Okay, so there's several questions that has to be done. You can try those questions on your own, but we're going to just continue with that discussion. And at the same time, I want you to watch the videos for chapter 4, which I've just covered. All right. So that's pretty much it for today, folks. So I'll see you guys next week. I don't know if I told you this, but your next test is your next test is actually next week. And what I'm going to do is I'm going to make it be based on chapters 1 and 2. So and I think I've given you back your graded assignments 1 and 2. Did I email you?
I haven't got 2
Just
yet.
one.
No chapter 2 yet.
Oh, okay, so hold on. All right, I'll take care of that. Shoot. Okay, I'll take care of that.
But the test is gonna be 1 and 2. you
Yeah,
said?
1 and 2, right? So like what we just did today will not be on that test, all right? So I'll make sure I thought I emailed it to you again, but okay. I'll make sure I get it back to you so that you have it to review in preparation for your first test, all right? And the test will be given in the testing center, so basically what you need to do is make an appointment. I think you got something, don't you?
Oh,
Good.
thanks.
So make sure you call and make an appointment. Not call, I'm sorry. You go to the website and make the appointment. And I don't know if I told you guys this, but I got an email from somebody at the testing center that said that in the past, they have had an issue with students making appointments but not doing their tests during that appointment, or basically end up missing when they should be doing the test, right? And that's an issue because the appointment slots apparently are very limited. So if you do not go and do your test, then basically you're making it difficult for other students in terms of making their appointments and so on. So if you can make a certain appointment as far as your test is concerned, make sure that you notify those guys so that they can make their adjustments accordingly. All right. Okay. All right, so that's it for today, folks. So I'll see you guys next week, Tuesday.
Who's the best this week?
Yeah, test next week. So you have until you have that week to make your appointment from the Monday to the Friday.
And then I just have one question.
Yes,
for
sir.
the lab today, cause I saw it was, there was one, the nomenclature.
Right.
Now, there was an experiment on there. We're not doing that experiment. Right?
What experiment?
There was a pre-lab on there.
I mean, the experiment that we're gonna do today is density, right?
That's,
Yeah.
Right. But
Okay.
when you talk about the nomenclature, the handout,
yeah, I'm just saying,
There's no
because on
experiment.
that, there was a pre-lab and post-lab on.
yeah, you should do those two, right?
Do the pre-labs do them?
Yeah, you have to do the pre-lab and post-lab of those. It's just
the nomenclature,
Just the nomenclature, right?
Oh, okay.
Nomenclature and all that, right?
Okay.
Yeah, yeah. What's up?
Is available to the testing, like locality sort of set B.
Oh, yeah, on any other camps.
Okay.
Right.
Okay.
Okay, you guys out there in Zoom?